nitrogen in order to build the most basic bits of life, like amino acids and DNA. But for most of life's history, converting nitrogen to biologically useful forms could only be
Don't
done
worry
by
about
bacteria
knowing
in
all of
soil.
this stuff, by the way.
They pull gas from the air and convert it to building blocks like ammonia and nitrates. That was until 1909, when German chemist Fritz Haber, with the help of a couple friends, figured out how to do it on our own. The Haber-Bosch process converts nitrogen gas and hydrogen gas, two simple ingredients, to make ammonia, which we can then turn into an infinite list of useful stuff. So why is this number one? Fertilizer. For the first time, farmers didn't have to rely on crop rotation or shovel what the family cow provided them to get nitrogen. Inexpensive chemical fertilizers let many people grow abundant food for the first time ever. The world grew so much food, in fact, that the global population has more than quadrupled since this chemical revolution. We make 450 million tons of nitrogen fertilizer this way every year. A full 1 to 2% of all the energy we use goes to this process. Now, of course, salad bars and cereal aren't the only thing that we make with industrial nitrogen. Nitrates are necessary ingredients in making explosives, and the Haber process allowed nations involved in World War I and II to unleash destruction on scales never seen before. But whether it was the battlefield or the breakfast table,
Just
that really
switching it
motivated
right
Haber
back
to
up to
harness
happy
nitrogen
times.
from air, one explosion definitely won out over the other, and it's just one delicious bit of chemistry that feeds our brains every day. Now, if you enjoyed these fine reactions, I know we skipped over a lot of important historical chemical wonders. So let us know in the comments what you...
Okay, that's good enough. Man. All right, WHMIS. So it stands for the Workplace Hazardous Materials Information System. And as of 2015, there are 10 symbols, which are these ones, which I haven't seen in a very long time.
I got this wrong on my test. I had one question, I got it wrong. It was corrosive and I put something else.
Oh, I see. Yeah, because for me, I had it where this one wasn't a thing, and neither was that one, and this one was toxic. But that was about it. But yeah, so anyways, we're gonna go right into practice. Yeah, so this is fun. So we're gonna go. So which one's easiest for you guys? That one's pretty easy. Yeah, that one's this one, right? And then corrosive is which one?
It's the third one. It's below the biohazard.
Word. Right there. Good. What about compressed gas?
Is it the bottle? Or like the bottom?
This one? Yeah. Yep. What about harmful?
The exclamation mark.
Good. Harmful or fatal?
The person?
This one?
Yeah. I don't know.
Not quite. It's
Top?
this one.
Yeah.
Yes, this one. That one's tougher to remember, honestly, for you guys than it was for me, because it used to be called poisonous,
See, that makes sense.
right? Like, anyways, harmful or fatal, I guess it's less scary. What about this one? What's this one?
That's the environmental.
Good. And then this one?
How?
Health hazard, yep. And then these two, which ones are these?
First one's flammable.
And the last one's explosive. Exploding.
This one?
Is that one not exploding hazard?
No, which one is this one?
I don't know.
Oxidized.
Oxidizing, that's the one.
I'm not good at it. I didn't do this.
I didn't do that, that's why I don't know.
It's okay. It's like, yeah, it's tough to remember. But yeah, this one, it might be actually easier to see if you're up close like I am compared to far away.
Looks like it's exploding.
But yeah, it's like almost like a sword is stabbing into a ball.
What is that one?
That one?
Yes.
That one is the exploding one.
Yeah, that makes sense.
Yeah. And then the oxidizing, it's the only one with a circle in it. So that's how I always remembered that one. And I guess the biohazard is easy because it's the only one with the black ring. So
Yeah.
that one's pretty good. But yeah. anyways, yeah, I don't know if I really needed those, but we got them right. So properties of matter. So we got some physical properties, which is like the boiling, melting point, the state, the color, physical properties of the chemicals. And the chemical properties, which is just like the reactions that the chemicals can have under different environmental conditions. And obviously to separate them, to separate physical things, I actually had to search this word up, but the can't, basically all it means is like if you have like, let's say you have like a bottle of, I don't know, like apple juice, but it's like the kind of apple juice that still has like the stuff at the bottom. Yeah, a little bit, kind of. It's like, well, not like in the, not like in it, but like, you know when you get, when you get like that like thick apple juice and it has like the stuff at the bottom? Yeah. Yeah. Or if you like, let's say like tea falls out of the tea bag when it's in your tea water and like it's at like the bottom, like the like stuff. Yeah, so the can, apparently all it is you like pour it, but the stuff at the bottom doesn't come out. So you like pour the tea water, but not the tea leaves.
Oh.
Yeah.
Is chemical just like if it can't be reversed?
And like to separate?
Like if it's a chemical reaction, it can't be reversed. If it's a physical, it can.
I would say that's true in most cases.
Okay.
Yeah. And then here we just have this nice little tree that I found online. No way I would spend in that much amount of time to make these boxes. But yeah, so we have matter here, which can be split into two categories really. Pure substances, which is basically just elements, and mixtures, which is a bunch of stuff put together. So if I said that I have a mixture of Gatorade, would that be homogeneous or heterogeneous? Heterogeneous. Or would it be homogeneous?
Which one is the one where you can like see the different?
Like see the different.
Like if it's a chocolate chip cookie, you see the chocolate in the cookie. Which one is that?
That's heterogeneous.
So it would be homogeneous.
Homogeneous, good. Yes. And if I said hydrogen, would that be an element or a compound?
Element?
Good, yes. Good. Also, this word here, colloid, all it really means is, you know how you have like hand soap sometimes, where if you pump it, it has like the beads in it? And they're like supposed to be like moisturizing beads or whatever, but they're just like, they feel weird.
Yeah.
Yeah, so basically that is a colloid because you have stuff that is technically suspended in another liquid, but it's not like dissolved in the soap, right? So it's just there. And that's what a colloid is. You probably will not need to know that on a test. But just in case that was confusing, because that was for me as well. Yeah. So that's just kind of easy little breakdown for that. And then we got some atomic models and another video, so I don't have to do that much talking.
Huh. 40% of 25 is the same as 25% of 40. After all these years, I finally understand.
Yeah, like two.
How do you picture an atom in?
This is like one. This is like the Bohr model and like the planetary model.
Yeah. I remember actually watching this video before.
Like this or like this or
Can you guys hear okay, by the way?
If you understand enough about atoms to visualize any of those things, then you know more about atomic theory than scientists did just 100 years ago. And like way more than they thought they knew 2,500 years ago. That's when Greek philosopher Leucippus and his pupil Democritus first came up with the idea that matter is composed of tiny particles. No one knows how they developed this concept, but they didn't think the particles were particularly special. They just thought that if you cut something in half enough times, eventually you'll reach a particle that can't be cut anymore. They gave the these particles the name atomos, which means uncuttable or indivisible. So basically they thought that iron was made up of iron particles, and clay was made up of clay particles, and cheese was made up of cheese particles. And they attributed properties of each substance to the forms of the atoms. So they thought that iron atoms were hard and stuck together with hooks. Clay atoms were softer and attached by ball and socket joints that made them flexible, and cheese atoms were squishy and delicious. Now this makes a certain amount of sense if you don't happen to have access to electron microscopes or cathode ray tubes or the work of generations of previous scientists. Because the fact is, atomic theory as we know it today is the product of hundreds, if not thousands, of different insights. Some models, like that of Leucippus, were just blind guesses. As time went on, many more were the result of rigorous experimentation. But, as has been the case in all science, each scientist built on what had been learned before. We've been talking a lot about the fine details of chemistry in recent weeks, and we're gonna keep doing that as we move on to nuclear chemistry and then to the basics of organic chemistry. But before we do, I wanted to set aside some time to explain how we know what we know about the atom today, and how we know that we're not quite done figuring it out. Now you might think that once Leucippus and Democritus came up with the general idea of atoms, it'd be pretty easy for someone else to take that little indivisible ball and run with it. But you'd be wrong. The next major developments in atomic theory didn't come along for nearly 2,300 years. I've already told you, for instance, about the French chemist Antoine Lavoisier, who proposed the law of conservation of mass, which states that even if matter changes shape or form, its mass stays the same. And you should remember the English teacher James Dalton, who determined that elements exist as discrete packets of matter. Thanks to these and other great minds by the 1800s, we had a better grip on the general behavior of atoms. The next logical question was, why? Why do they behave the way they do? This led to the investigation of atomic structure. In the 1870s, scientists began probing what stuff was made of using discharge tubes, basically gas-filled tubes with electrodes at each end, which emit light when an electrical current passes through them. Basically what a neon light is. Because this light was originally produced by a negative electrode, or cathode, it was called a cathode ray, and it had a negative charge. But in 1886, German physicist Eugen Goldstein found that the tubes also emitted light from the positive electrode, basically a ray heading in the opposite direction, which meant that there must also be a positive charge in matter. Goldstein didn't fully understand what he'd discovered here. I mean, scientists still hadn't figured out what was responsible for the negative charge in the rays either. Then, English physicist J.J. Thompson took the discharge tube research
He's
further.
important.
By measuring how much heat the cathode rays generated, how much they could be bent by magnets and other things, he was able to estimate the mass of the rays. And the mass was about 1,000 times lighter than hydrogen, the smallest bit of matter known at the time. He concluded that the cathode rays weren't rays or waves at all, but were in fact very light, very small, negatively charged particles. He called them corpuscles. We call them electrons. So even though we didn't understand what shapes they took, we knew that there were both negative and positive components to matter. The next question was, how were they arranged in the atom? Thompson knew that the atom overall had a neutral charge, so he imagined that the negatively charged electrons must be distributed randomly in a positively charged matrix. And the very English Thompson visualized this model as a familiar English dessert: plum pudding, the positive matrix being the cake, and the electrons the random floating bits of fruit within it. Even today, Thompson's model of the atom continues to be called the plum pudding model. And while a single electron's motion is random, the overall distribution of them is not. The next big step was taken by New Zealander Ernest Rutherford in 1909. He designed an experiment using an extremely thin sheet of gold foil and a screen coated with zinc sulfide. He bombarded the foil with alpha particles, which he didn't really know what they were, just that they were produced by the decay of radium. They were positively charged and they were really, really small. He expected them to just fly right through the foil with no deflection, and many of them did just that. But as it turned out, some of the particles were deflected at large angles, and sometimes almost straight backward. The only explanation for this was that the entire positive charge in an atom, the charge that would repel an alpha particle, must be concentrated in a very small area. An area that he called the nucleus. Because most of the alpha particles pass right through the atoms undeterred, Rutherford concluded that most of the atom is empty space. And he was correct. Rutherford would later discover that if he bombarded nitrogen with alpha particles, it created a bunch of hydrogen ions. Now, he correctly surmised that these tiny positively charged ions were themselves fundamental particles. protons. Now we're getting close to reality. So these chemists had a fairly good idea of the structure of the atom. They just needed to figure out what exactly the electrons were doing. Enter Niels Bohr. In 1911, the same year the results of Rutherford's gold foil experiment were published, Bohr traveled to England to study with Rutherford. And as a physicist, he was also interested in the mathematical model set forth by German physicists Max Planck and Albert Einstein to explain the behavior of electromagnetic energy. Over time, Bohr came to realize that these mathematical principles could be applied to Rutherford's atomic model. His analysis of the gold foil experiment, calculations based on the proportion of alpha particles that went straight through, those that were slightly deflected, and those that bounced almost completely backward, allowed him to predict the most likely positions of electrons within the atom. Bohr's resulting model, sometimes called the planetary model, is still familiar to most people, probably including you. It represents the electrons in orbits around a small central nucleus. Each orbit can have a specific number of electrons, which correlates to the energy levels and orbitals in the modern model of an atom. And while it's definitely flawed, Bohr's model is very close to reality in some important ways. But like everyone I've mentioned in the past couple of minutes, Bohr was at once fantastically right and way off. The problem was those pesky electrons. It was the German theoretical physicist Werner Heisenberg who got everyone to understand just how huge and mind-blowing this electron problem was. But he was also the one who helped tie the whole mess up into a neat little bundle. Using his wicked math chops, Heisenberg discovered that
Did you learn about him?
with certainty both the momentum
Yeah.
of an electron
No?
or any...
Okay. Well, we will stop right there then because it will be very confusing.
Going back and forth from
I have a question. So
Yes.
Rutherford was the planetary, and then Bohr was like the Bohr model?
So Rutherford was the, where was
Atomic
he?
particle?
I
Rutherford,
didn't hear which one he was.
because Thompson was plum pudding.
Yeah, I got that one. And then
Um,
the Bohr model.
So,
Mars the gold foil with alpha particles.
so Rutherford's,
That's the experiment he used. But that's not what
Here.
the model was called. And then who was the Marvel model?
the which one?
The Marvel one, like the very, very first one.
That was Dalton. Okay. So this is So this is what the Rutherford model would look like, and it's just basically what. He's big on TikTok now too. Can't remember his name, but he's just basically saying that the positive interior is what he found, because before he came along, all we really had was the Thompson model, in which the entire like inner part of this like black outline was positive, and these negative things were just like the chocolate chips kind of thing. If you look at this, like a positive cookie, negative chocolate chips. Because with that experiment that he did, he had that gold foil, and he basically, like, by shooting these basically protons into this positive foil, some of them went through, obviously, because an atom, all of this space, right, the majority of the space that an atom takes up is just electrons, and it's not very dense at all. But this part is very dense, but it's very small.
What was it called? The planetary model? Is that what his was called?
I think the planetary model, he called it the, I think the other one, Rutherford was the planetary model.
Yeah, so that's him.
No, sorry, Bohr was the planetary model. Rutherford, sorry.
But Bohr was the Bohr model. Called it after, he named it after, do you know?
So the Bohr is sometimes called the planetary model. It's just think of it as like the Bohr model has the rings and the Rutherford doesn't.
And then what's the Rutherford one called? Is it the cloud one? Rutherford model?
That's a good question. Let's see. Nuclear atom? Did it have a name when your teacher taught it?
Well, there was one named Bohr, one planetary, one plum pudding, one marble, and one cloud. There was 5.
That's what you
Okay.
Yeah.
And that's not how
So I think the planetary one was this one, because it says Rutherford atomic model or planetary model. Like if you go back, it says planetary model as one of the descriptions.
That is true. That is true. Okay. Yeah, I think. I mean, it obviously depends more on the way that your teacher uses the terminology. So if your teacher uses a specific term to describe a certain model, then I would use that term for sure. Because in this case, right now we have Rutherford according to Britannica being called a planetary model, but we also have Crash Course saying that it's the Bohr model is the planetary model. So I think it's very much just there's the Bohr model, Rutherford model, and if you just keep it to the names of the people who like discovered and created the models, there shouldn't be any error in terms of
But on the
marking.
test, like on the final exam, if it's planetary, do we refer to the Bohr or the?
Look on the sheet, did you not get a sheet of it, like, of each model?
Yeah,
an
but your class
example?
is different than mine.
Do you want my sheet?
Do that, yeah.
I'll
That's
take a
smart.
copy and send it to you.
Yeah, that's smart. Because if I looked it up here, I could get like a bunch of different
Like, I just had a
charts,
picture,
I
like,
guess.
The picture of the model, the name, and like, who made it.
Hmm.
for all of them.
Okay. Unfortunately, I cannot answer that for you. Sorry about that. But yeah, so those are just the atomic models. Do you have any questions so far, other than more like general like naming terms? No, so far so good. And Wemyss, all right. All right. Is this where I said no? Break was after this. Okay, yeah. So here we just have the periodic table, just very general. We got the metals on the left of the staircase and the non-metals on the right. And then groups and families and periods, obviously. We have some information that we can derive directly from the element symbol itself. For example, the atomic number. What's something we know about that?
Number of protons.
Number of protons, good. And then here, I don't know, can you see the pink?
Yeah.
But it kind of goes like this. But yeah, so basically those metalloids, have you ever seen something in a test where it's like copper and then they have brackets and it's like 2 or 3 in Roman numerals?
And they have like 2 different charges.
Yeah, so that's just what those metalloids are right there.
So only metalloids have 2 different charges?
Or sorry, the transition metals. Sorry, transition metals have those. My fault. Yeah, so that's just the purple box there. The metalloids are just, they have metal and non-metal properties. So that's why they're kind of separate. They're just a little bit different. And then halogens, obviously, are these reactive or unreactive? The blue box.
Reactive.
Very reactive. What about these ones in the green box?
Reactive.
Non-reactive. Non-reactive. And then these guys here, is period or family or group 1 or 2 more reactive?
2? I don't know.
1.
Number 1, yeah, because number 1, it's okay. It's just a lot of memorization basically. So basically, period or family 1 or group 1, excluding hydrogen here, because it's obviously on both sides, right? But this row or column, is it row or column when you go up or down? I never knew.
I think column is like this, row is like
Okay, so if we look at this row,
I think it's the opposite. This column is like.
whatever, it's pure family.
so if you look at this family number 1, in here they have elements such as like, we got lithium, we got sodium, we have potassium in here, like lots of really reactive metals. I don't know if your teachers have ever mentioned this, but the reason, like sodium itself is a metal that we have to store inside like oil because it is so reactive that even holding it in the air, it will react with the water from the air just holding it. So it's very, very reactive in this column right here, and that's just because it has that one extra electron in its orbital. So it wants to get rid of that, so it just reacts very quickly with everything. So for example, a very common one is you'll see sodium from this side reacting with chlorine, which is right here. So two very reactive, very, very reactive elements reacting to form table salt, right? So that's kind of cool. But yeah, those are just called the alkaline metals. Any questions regarding any of these things?
From like the blue, like the alkali metals, which one's the earth alkali metal? Is that the second one?
Like which one of these two?
Yeah, the first one is earth ones and the second is regular?
I think
I
so.
don't even know.
I think
It was
so.
on my test, but there's like a giant periodic table in the back of the class.
Yeah,
With,
same.
like,
Yeah. You're so mad. You forgot to take it down.
No, they can't take it down because
That was so
they
nice.
share the classroom.
I love it so much.
So like everyone was just looking back to see which one it was.
Okay, so the family 1 is the alkali, and family 2 is the alkali earth metals. Yeah.
Okay.
Yep.
That's what I needed to know.
Awesome. Perfect. Any other questions?
So noble gases are non-reactive.
Yeah.
Halogens are very reactive. Then alkali metals are very reactive. And then alkali earth ones aren't.
They are still
They
reactive.
are,
Yeah.
just not as much.
These two families right here are reactive. Yeah.
Which is
They're
weird.
just, this one is like slightly more reactive. Yeah.
And
Yeah.
do you tell like how reactive it is by the charge? Or how do you
No. So you would. I don't like. Do you mean like would we determine the strength of the reaction if it were to react?
like if one is more reactive than the other, how would you know?
If it was.
Yeah.
Have you had like a question like that on a test?
No, I haven't. I just want to know.
Okay. I don't think you'll need to know that in Science 10. I just realized this isn't my computer. Hold on. Yeah, I don't think you'll need to know that, but I'll get back to you for sure after the break. I'll just look it up quick on the program of studies, but I don't think you'll need to know that. If anything, it'll be top to bottom, will be stronger to weaker.
Okay.
Yeah, stronger up here, weaker down here. But that's something that I learned in university. So you don't need to know that. But yeah, it has something to do with size, basically. But yeah, so that's those. Now we're going into atoms. So you got the nucleus, which contains the protons, which has a positive charge, and the neutrons, which have a just completely neutral charge. So the number of protons, like you're saying, equals the atomic number. So that's a very quick and easy way to be able to tell. Outside the nucleus, in those shells, those energy levels, if we kept watching on the video, he would just basically talk about like an electron cloud forming, where it's just like areas of where electrons are theorized to be, because we can't actually tell. But electrons don't have mass because the mass is so incredibly small that it just doesn't matter. Well, can gain or lose in ions. In an element, protons and electrons are equal because it is just neutral. So like hydrogen and oxygen on the periodic table, stuff like that. Are you guys familiar with diatomic atoms or elements? When I say that term, diatomic?
I don't think so.
I know I learned this, I just don't remember.
Yeah.
Okay, we'll touch on it a little bit later, don't worry. Awesome. All right, so all good with this slide here. Is pretty straightforward, lots of writing for not a lot of information, to be completely honest. Isotopes, all right, they have fewer neutrons in the nucleus than normal, which changes the atomic mass. Sorry, more or fewer. An interesting example of an isotope is if you guys have heard about heavy water.
Yeah.
So heavy water, essentially all it is it still is water, and it looks exactly like water. It has the same, it's very similar physical properties to water. But if you put ice of heavy water into water, it'll sink.
I saw a TikTok of that.
Right? Okay, I think we saw the same one. Okay, never mind then. But I thought that was crazy because I was like, no way it sinks. Anyways, but those are just what isotopes are. There are a couple of carbon isotopes that you will learn later on if you go into organic chemistry, and a couple more hydrogen isotopes as well. But yeah, overall, you just essentially need to know that an isotope has more or fewer neutrons in the nucleus. And if you have more or fewer neutrons, it doesn't change anything really in terms of charge or anything like that. It just changes weight because neutrons have no charge inherently. Next, we move on to ions. So metals, sorry, when I said the previous slide there, hold on. I think I said, when I said these guys, I think I said they have an extra. They're actually one down, so they want to gain an electron. They don't want to lose one, they want to gain one. These are the ones that want to gain one. Or sorry, did I mess up again? Hold on. Metals lose. Yeah, so these guys are going to lose the electrons and these guys are going to absorb them. Yeah, perfect. Yeah, so just to clarify that, because I just wanted to go back. So yeah, metals lose electrons to make cations, and non-metals gain electrons to make anions. So that's why in solution you'll see like H+, O2-, stuff like that. They do this to fill their outermost valence shell of electrons to become... This is embarrassing on video. So I was right the first time, actually. These guys do have an extra electron, and then losing that gets them into that balanced state, that state that they want to be in. These guys have an extra electron. They want to get in to have the same amount of electrons as these guys. So if you see, like, for example, element number 11, it wants to lose one of those extra electrons because it has 11 electrons and 11 protons to stay neutral. So it's going to lose one of those electrons in order to have 10. And that's going to be a very stable state for element number 11. Because if you have an element number 10, it's a noble gas, right? And that's why this is so reactive, because it wants to become stable like the noble gas, which has a full valence shell. Same with why halogens are so reactive, is because they want to gain that extra electron in order to become a noble gas state. There we go, finally made it. No longer confusing for me either, hopefully.
It's like ions, the thing where, let's say, the atomic number is 2, right? And it's -1, then if you change it, it'd be like 3, and then if it's like +1, it changed to 1, like...
So, sorry.
No.
Can you...
This thing when, with the formulas, if there's a certain charge, like 2+,
Mm-hmm.
and then the atomic number is like 13, if it
Okay.
was 2+, then you'd lose 2 and it would turn it into 11, and then if it was 2-, then it'd add 2 and it turned it into 15. It was something
Wouldn't
like
it
that.
just go like the easiest way to make a full valence shell?
Yeah.
Add or subtract?
Yeah. So if basically, I think what you're saying is right. So yes, if you have, let's say, right here, number 11, this one has an extra electron, so it's going to go -1 to go to 10.
1 plus, it switches.
I think so. I don't want to say something to confirm something that could be wrong, but
Like
if...
Like 4, I could lose or gain is the same.
So this one is going to go back to try to become 2. So it's going to lose 2 electrons. To get that, it's going to lose those 2 electrons and get that full valence shell and that inner valence shell. Because this one only has that inner valence shell filled, right? And it's going to lose those 2 electrons rather than gain 6, right? So it's going to go the shorter way. I wouldn't go as far as this row to be like, would it lose 3? Because most likely it wouldn't. It's pretty stable with those 3 electrons. But these guys will be more keen on either losing or gaining electrons. So these 3 rows here. 1, 2, and 17, those are the fun ones. They change. The other ones stay pretty the same. Awesome. Finally, we made it. Perfect. Last bullet point. The first shell fits 2 electrons, the second shell fits 8, and the third shell fits 8, etc.
And then if it's 4th and we don't know, is it just 8 or do we just say like...
I don't think it'll go that high. It shouldn't.
Because like, can I see a go? Because I had a test, like the dot diagrams where you draw the valence shell? Like some of them have like
Goes 1, 2,
like 52 electrons.
Mm-hmm.
So it would go past the third shell. And I drew 8 because how many would be like in the last one. And she said it was not right. So how many would we have to do for that?
Okay, so let's see. 4th shell. Sorry, I haven't touched a lot of this in a while.
But it wouldn't be the 4th because there's 52. You need way more than 4.
I just want to see like if it has... Okay, there we go. The 4th shell holds 32 electrons. Wow.
Is this your like the AP chem part?
No, this is regular chem. We have questions for...
I didn't do that.
You have to draw this one. And
Oh,
then,
this dot diagram?
yeah.
Like the 1, 2, 3, 4.
Yeah. Except for the 56 is like the 19th shell.
There'll be a lot of dots.
Right?
I think
She
it
told me
said...
to just draw 8 if there's more than like if there's 56, just draw 8 like it's the last third shell, and then the rest you don't know. So you can't draw it.
Okay. So she just said like draw enough until there's the third shell filled until
Yeah,
8?
Like if there's more than, because in total that's 18. So if there's more than 18, just draw 8 and just, that's it.
That's it?
Yeah. So the 4 shell, I don't know how many it holds.
So I would just do that because the reason I'm hesitant is have you done anything about like 1s, 2s2, 3p orbitals, stuff like that?
Oh, the like line, the thing.
Mm-hmm.
Like the 3 lines. That one's like 8872, I think. That's how it folds.
It's like this kind of stuff. Electron configurations.
No, I haven't.
Like these numbers here, they don't look familiar. Okay, yeah, good. Because that's really how you determine how many electrons there are in a cell. This is just more of a simplified version. So I would honestly go by what your teacher is saying, and if there is more than those 18 electrons, like in the element, then I would just leave it as
8.
the 18.
Okay.
And just be like, hey, I don't know where they else go because you haven't taught me, kind of thing. If I went on Google, it said 32. For some reason, that seems like an extraordinary amount to increase.
Yeah.
But I don't know. I don't know. Or maybe your teacher's just trying to save you from drawing 32 dots in the fourth shell.
I don't do that on my test.
I just assumed like they all had 8 after the first one, so I like
Mine had like
calculated it to see how many.
And that's what this is also kind of showing that it assumes too, right?
Yeah, that's why I thought about that.
Yeah, I don't know. Let's see. I'll actually search up a different question.
Did you do the thing where it was like this, 2,
Oh. So it goes 2, 8, 32.
and there was a third one with the maximum, I think, 8?
This one's also 8.
Okay, so wait. So it's 2, 8, 32. And then within those, it goes SP
Oh, it's 2, 8,
stuff.
you're right.
Each. Yeah, I would honestly clarify with your teacher about this.
Okay.
Because according to this, it would be 1. Yeah, I don't know. 2, 8, 18, 32. Does that seem familiar?
No, it's 2, 8.
Well, then it wouldn't it just be like 18 minus 32 and then just that? Like 32 is how many electrons you'd have after the 4 shell in total?
So what this is saying is in each shell, so the shell number 1 can hold 2 electrons. Like here. I think this will be easier. So it's like if we have the nucleus here and we got this thing, it's saying like this, and we got here like 1, 2, 3, 4. And then this guy, it's saying we have 18.
But it's supposed to be 8.
I like the thing is I don't know which one is the one that your teacher is going off of, because this one for me is the one that I find the most familiar, but I don't remember back until grade 10 when I took Science 10 to remember which ones they used. Because I also remember them saying just use 8, right?
Yeah.
So that would be something that I would just ask your teacher about. Sorry about that. Okay. But yeah, other than that, interesting. Okay. Other than that, are things going okay so far?
Yeah.
Okay, perfect. Everything's making sense. I'm not contradicting anything too much.
Yeah.
Okay, perfect. Awesome. Okay. All right. So we have different kinds of compounds. So we have, what time is it? Okay, so I'll just do, okay, we'll actually we'll stop here because it's actually naming. So we'll take a bit of a break.
I'm just confused because that's what I put in mine.
Yeah, so I'm wondering if it's just like after 3, just,
Because she said that like we don't know exactly how many, so we just end up doing, like you just put 8 as there's like over.
mm-hmm.
Do you want a slice of pizza?
Oh, sure.
You go.
No, I'm not taking the first slice. You guys should have that. But so far, like, this is stuff that you guys have learned too.
Yeah, we've done
Okay.
all of it,
Okay.
yeah. Chem was like the easiest one.
Okay, that's good. That's good that we're starting there then.
Yeah, chem and like bio for me are good, but physics, oof. Physics.
I was like, me too.
Chem is the only good one.
Like I love bio right now. I'm doing so good at
I
bio.
hated bio.
No, we also just
Oh, yeah?
bio.
Chem is 3 days of bio and it was game over.
Yeah.
Bio is fast paced. I was actually at Central doing my practicum last semester, or like a couple months ago, I guess. And yeah, Bio 22, same thing. It's just you miss a couple days and you miss like half the unit.
Yeah.
It's crazy.
3 days. It's okay, I was worth it.
What did you end up doing instead?
I was in Mexico.
Oh yeah, that's definitely worth it.
Yeah, so much better than bio. The bio's like fun. Like it's
Bio is not fun.
compared to physics. Holy, physics sucks.
Physics is kicking my ass.
Me too. The unit test is so hard. Wait till you have to write it.
You know what?
Holy.
You can't even say chem was easy, okay? Remember your AP chem test?
Okay, but that doesn't. I cheated and still didn't get 100. I got 87. I got 7% the first time.
Oh.
But I didn't know we had.
So if you think about it, that's a big upgrade.
Yeah, but I got the answer key from the test. And my mom doesn't know that. But okay, to be fair, it was AP, so it doesn't go towards our grade.
Yeah.
And I didn't even know we had a test that day.
Okay, so then yeah, you can't really.
Like, I didn't even study, and I don't pay attention in class.
Okay. Your mom's on stuff though. That was the best thing ever.
No, it was not.
No, I told you not to come
She was
home.
pissed. I should have not came home. We should have texted.
I did text you.
You didn't call me.
Well, I can't call you in front of your mom and say, don't come home. It doesn't work that way.
Oh, you could have.
I tried my best, okay? I would never done that.
No, that was funny.
You would be sleeping on my couch. You have a good couch. No, I didn't.
Where's the heat taking us?
Put in Charlie.
Reservoir?
Can't pay for Dawn until now.
Oh, how about I just pay for your dog?
Deal.
Okay.
I have the 11 cents too.
No, you owe me 11.
Oh wait.
Subtract 11.
No.
You have 389.
No. You know what? It was my mom's 11 cents. So.
No, it was mine.
11 cents.
She gets pissed over it too.
It's funny. We went to Co-op to get ice cream. but
As you
we got
do,
a little
yeah.
More than ice cream.
Okay.
And
A
I
little
had,
more.
I had a $20 bill from my mom. And it was 2011. So
Oh.
You know what? You work, okay?
You work
my,
too.
My manager's taking rap on me though. Because I booked off so much time. So he's just not scheduling me at all.
I would do that too.
It's not my fault I have exams.
But you're not gonna study even if you book
That's
off.
true. Every single test.
This is awesome because I'm literally hearing the exact same thoughts. It's like deja vu from when I was in high school. Yeah. I would do the exact same thing. Like, I'm going to be honest, like, my physics 20 grades, I dropped out with a 43 halfway, not even halfway through the course.
Our parents would kill us.
Oh, mine almost did. They called the school.
No shit.
I did good. Like in physics, I did really good on the quizzes, and the unit test was so hard. I did not do good.
In chemistry, I did good. I had 90s in chemistry.
The Science 10 physics, I will be able to teach you for sure. But if it was physics 20, that would be tougher, yeah. Oof.
Physics, that one's hard.
Oh, so that's why you wanted to do physics?
That's my bio final. That's what I wanted to do.
Oh, wow. I had my chemistry final, so. I'm just kidding, I didn't.
I don't know. Chem's pretty easy so far.
I don't like bio.
Like this year, it was so easy.
That's
I
good.
had bio. Bio's also
I
really
want to
easy.
drop bio.
If you do Bio 20, you'll really like it.
I'm doing bio 20 and 30 next year.
Both?
Because it's AP,
I'm
so
doing
it's like...
all three.
Mm.
Chem, bio.
Yeah, and I'm doing... how hard is physics 20? Is it really bad?
It's the same as bio, it's just a lot in a short amount of time. And as long as you study for the right units before you take the test, you should be
do
fine.
that?
Yeah.
I mean, I don't study, so it's a bit of a problem.
Well, I mean, it's just because in chemistry,
But not.
there's like this handy thing called unit analysis. I don't know if you've heard of it. If you haven't, you'll learn it next year. It's really fast and easy. And I would try to use it in physics, but you can't in physics or something, like it doesn't give you the right answers. So it just never gave me good marks.
Maybe it was the teacher's fault.
I do blame her 100%. She sucked.
I blame my English teacher.
My science teacher's so bad.
He was hoping on my downfall.
Like every time I do good on a test, she's like, you know, I doubted you, but you did good. Like, shut up.
Dude, that's basically leave the class for the
Yeah, I'm not in class most of the time.
No, our math teacher hated us.
But we ended up doing good, so it's fine.
Well, that's all that matters.
I can't focus in class. There's too many distractions.
In math?
Like
we
the
were-
nice beige walls
You
and
would, like,
arrow
teach
slit
us?
windows.
No, we don't have windows in our school. There's like 2 rooms with windows.
Oh.
I have architecture, and there's windows in architecture. They're always closed. It
I
doesn't
love
even open the
architecture
blinds.
so much.
It's
That's
so boring.
You can take it next year?
I'm dropping it.
Wow, savage.
How are you dropping architecture?
I have enough credit.
I didn't do anything in architecture, like I'm 99.
I have 100 in it right now.
Went to the final house. And CAD. CAD is nice.
CAD makes me want to off myself. So bad. So boring. Like, the final, I already did the final house.
Was it graded?
No.
There you go. You're making a scholarship money for it?
Yeah, did you know the build house contest?
Mm-hmm.
Alec got 3rd place.
You?
No, Alec. The Flash.
You got 3rd? Who got 1st and 2nd?
These other 2 kids in our class. They got money for it.
You probably
You-
tryhards. Oh, I hate tryhards.
You're a teacher's pet, so you know better.
I don't try hard, but I'm not even in class.
Yeah, it makes it a little difficult.
You know what? The skills over math though was insane.
My skills carried you.
Yeah, they did.
Let's do this. Our teacher, he like doesn't care. Like we were writing a test, you know, like domain and range.
The like X
He
dash.
doesn't know how to do
I don't
that.
know how to
So I
do
finish
it.
my test and I take my like big piece of paper and write it out big and hold it up for her. So on the test,
She's holding it like this.
like this, and I'm not even
writing
trying to hide it. And she's just like on the test, like looking and copying what I'm holding up, and he like doesn't care.
I got it right. Okay.
Yeah, I think that's
Wow, what a guy.
Yeah. I hope
He
you're
was a
not
legend.
But he's so boring.
As soon as he stopped talking, we were out.
Yeah.
When he talks, you're like asleep because he's so boring.
You know what I do though during architecture? I go to get cookies. Like I just walk to the plaza to Subway and get like the 12-pack of cookies, and then like 5 minutes later I walk back into class and he doesn't notice.
He doesn't care. Kale did that too.
Like he doesn't notice. We don't do it. Like we switch every week.
You do it every week.
Yeah, it's
Does
like
your
a
mom
hefty
care?
investment.
Which is there.
She'd be happy I'm eating.
Because in that class you do nothing.
That's true.
It's like gym.
Gym, I think what I did for gym was I showed up for attendance and then I'd walk around the school the rest of the period.
How would you skip gym? You skip like English, like
It was
really
so
boring.
boring. No, English I can't skip.
Why?
Because I was failing English. I'm
I don't
telling
know how
you,
I'm doing good in
he
English.
was hoping on my downfall.
My teacher just liked me. 'Cause
He
I'm so
like
bad.
he chose favorites. Like I used my friend's work and she got 100 and I got an 80. Like all I did was paraphrase it. And like it was the same with Old. Even Old did better than me. And Old didn't even turn in his assignments.
I got a 93 on those notes.
Out of 27
But my
pages of
teacher
those
likes
notes,
me.
and I did it
Like I read the
before I was
essays that I
failing.
do, like I got 75 on my essays, and I read them and I like can't read them. Like I don't know how she gave me a 75. Like,
Oh,
I
wow.
don't even know what I wrote.
I don't know what you wrote at the time. I'm trying
Yeah,
to
it's so
figure
bad.
it
Even when I
out.
was texting her, she can't even read it.
I'm like grammar.
Wow.
Wow. That's awesome. Good thing this is not English.
I'm passing. That's what matters.
I made like English from this summer.
Oh, yeah?
I'm going
I'm
to
getting
gym.
rid of it.
That's smart. That is smart. I should have done
No,
that.
because I went to guidance, they called me down, they were like, according to your grade, this isn't the wisest decision for you. And I straight up said, I don't want to sit through another 4 months of it. And then I think they gave it to me.
I want to do social in the summer, but I don't know if I got it. Because we still haven't go.
I also
Oh.
signed up for COM on the Vista Learning thing.
You can't.
It's not through CBE.
So you can? You can do com and?
Yeah, it's through different, so CBE do like a
Yeah, but do you have to
board.
go in person for it then?
No, it's online. I signed up today. I
Kidding.
hope I get it.
Tell me how.
Does it transfer?
No, it's online.
But like, does it like give you credits that will show up on your transcript?
You get more credits doing it online than in person.
No, you get 3 credits doing it.
No, because you go to the camp and then you get 5. You know,
No,
you go to
I'm
camp.
not doing the camp. It's just a course through the month.
Oh, you don't do the camp?
Yeah.
Oh, okay, that's, yeah.
Okay, never mind.
There's like a camp, that's a goalie camp you go to for a
I
week.
don't want to do
And then you
the
get 5 credits instead of 3.
Interesting.
I don't want to do the camp though.
It seems fun, like you get like horseback riding and stuff.
Huh.
It does not seem fun.
The things you know, or I guess learn. But are we ready to keep trucking along? We got 8 more slides, and then I have a hefty book for you guys to work through.
We're ready.
I'm so excited.
Big practice.
I'm gonna come home with the box of these.
I made all of these questions.
Yeah.
Hmm.
You made them all?
All of them. Every single one of them.
Good job.
By hand. And I actually freehand drew that little comic there too. So,
Nice.
yeah, just multi-talented, I guess. Anyways, compounds can be ionic or molecular. Do you know what the difference is?
Isn't ionic like a non-metal and a non-metal? While molecular is a metal and a non-metal. But then can ionic be like a polyatomic and
Covalent bonds are shared.
stop reading your notes.
So ionic is a metal and a non-metal, and molecular is non-metal and non-metal, and the polyatomic ions can be ionic or molecular. The polyatomic themselves aren't a compound. That's just think of it as an element, like PO4 or SO2 or something like that. That's like one thing. And it's just going to be like that thing could be in an ionic compound with like magnesium or something, if you wanted to.
So if it's with a non-metal, then it's molecular. If it's with a metal, it's ionic?
Yeah.
Okay.
Yeah. So if you see a metal right away, ionic.
Yeah.
Yeah. Some properties are.
Names too. Like when you see the names, it'll be like iron 3 nitrate or something.
Mhm.
Iron has two charges.
Yeah, but like on some of them, it'll be like the prefixes.
So I know what you mean. So it's actually really easy to remember, and That is if I understood the 7-minute video that I watched before driving over here. But ionic, ionic bonds, you don't actually have to add like di, tri, tetra, or mono or whatever. That's just the molecular. So it's literally just going to be like, it would be like magnesium sulfide, or that would be
And
it.
if you have like, because you write for molecular, you write. So the first one, if it's 1, you just don't put mono, but the second one, if it's 1, you put mono?
For molecular, yes.
Okay.
And for ionic, you don't even worry about it. Yeah, awesome. But yeah, another thing is if you don't have a metal, you will not be able to conduct electricity. Yeah. That's basically what electrolytes are. All right. So this is just found in your data booklet, I think, if you have one, right? Do you have a data booklet? No. You have to memorize everything?
Yeah, but I kind of just text them to myself.
What? You don't get a data booklet?
Do you still have it on your arm?
Yeah, this marker will not come off. I like wrote stuff for my bio exam and it's still there. It was a week ago. I'm never using that Sharpie again.
Yeah, I wouldn't either. What the heck?
I just text it to myself, like onto my watch.
A girl got caught using her watch and she got a 0 in my class. Just saying.
That's rough.
Yeah. Miss Young, oh, she's awful.
Bro, I've seen like she makes everyone put their backpacks up.
Yeah, and then if you want to go to the bathroom, you put a bunny on your desk. Like a stuffed bunny. So when I'm out for 20 minutes, everyone's like, I'm Calvin. Once I went on a walk and she was waiting outside the door for me.
It's like your mom when you came home.
Interesting. But yeah, so, okay. Also, these ones here, these are diatomic or polyatomic elements.
Okay, so there's like, is it like,
So the most important ones are going to be this guy right here to hydrogen. These guys right here. And if you'll see it, it kind of makes like a 7.
hockey puck? That's what my teacher
A
called it.
hockey puck.
Yeah, so it's like from carbon to iodine is 2, and then phosphorus, because a spider has 8 legs, so S8, and then phosphorus is pony, so it has 4, and then hydrogen is 2. Right?
Wow.
What?
That's
'Cause-
what told me to memorize it.
Do you know how?
Because I just look at it like this. Oh, whoa.
Yeah, it's like
Just
that.
like this, yeah. Is that a hockey puck though?
That's what she called.
That's not a hockey
Not a puck, a stick.
Oh, okay. I was like, wait. Are you just like thinking like it's like 2 rows? Like I got a picture.
Teacher said to memorize it of like have no fear of ice cold beer, and then you just remember that P has 4, a spider has 8 legs.
Yeah, just carbon to iodine.
Yeah. Yeah. And then the O3, what is that?
Oxygen.
Is it? Is something that is way up there. We have a layer that gets holes in it sometimes and it makes the news. It's big in global warming. It's a greenhouse gas. It has a Z in its name.
Oxys.
Ozone. Have you heard of ozone?
Ozone?
Oh.
No, we have O2.
Yeah.
We don't
O2 is polyatomic. Ozone is just like that layer that surrounds the Earth
Oh, yeah.
to keep the atmosphere
Like holds the
in. Yeah, exactly. Yeah, and that reacts with things like nitrous oxide. Wow.
What is P4? Phosphorus?
Yep.
P4 is phosphorus, yes.
And
I wouldn't worry about memorizing all of these per se. So, if anything,
These have to be memorized. I could never memorize these. These were always on my arm for every test. I did
Really?
2 of
oh,
these.
you like you actually have to memorize all of
Yeah.
these?
all
Use
of
on
them.
the calculator.
But like,
Oh.
some of them are on the formula sheet. Like,
And
there's
yeah.
2 of them.
It's
Okay.
methanol and
Yeah, methanol and ethanol are on the,
Formula sheet.
but the rest you have to memorize.
Okay, so what is this one?
Which one?
This one.
Water.
Water. Hydrogen peroxide. Yes. This one?
Nothing. No, wait.
No.
That's the wrong one.
It's you're close. This one is
Glucose.
in P.
Oh, it's sulfuric acid.
Ammonia.
Yeah, that's what.
So think of the only one with the nitrogen is the one that's ammonia.
It's on the periodic table.
No, it's ammonium on there.
It's ammonium because it's NH4 plus, right?
NH4 and then
Yeah.
ammonia is NH3.
Yeah. And what is this one?
Bring your own.
What is this one?
Ethane.
No.
No, that's
Which one is this one?
sucrose.
Sucrose. What's this one?
Glucose.
Glucose. Good. This one?
CH4 is
Sulfuric acid.
methane.
Methane. Then we have almost one more carbon than ethane. It starts with a P.
Propane.
Propane. Good.
Oh, we didn't have that one.
No? Okay, so it might just be a mistake, and it might just be for ethane
We
then.
have water, hydrogen peroxide, methane, methanol, ethane, sucrose, and glucose.
Okay, and then these guys, you guys know.
Oh, wait.
Methanol and ethanol, wow. But yeah, so the main important one I think that you need to know is definitely glucose, especially since photosynthesis. And then water, obviously, that one's easy. Have you heard the joke where it's like, the scientist walked into the bar and said, I'll have H2O. And the other scientist walked in behind him and said, I'll have H2O too. And he died. Because if you drink hydrogen peroxide, you're dead.
See, I don't
yeah.
I don't remember how to get back into the memory thing on these calculators, but I have like it all written on my calculator.
If you can find it.
Well, no, because I knew how to do it during the test. Like this was
Oh, I see.
in January, because I haven't done chemistry. Like it was my first unit.
Yeah.
So I had it all written down, and so now I don't remember how to access it, but I did. And someone just wrote everything on the calculator, and I just had it all. I didn't say anything.
You have to clear our calculators. I don't know how you do that.
No, I haven't had to clear my calculator once.
Oh, I had to clear it before every test,
We
yeah.
had to in math.
Well, I have to in science too, but my teacher.
Maybe it's just AP stuff.
Yeah, my teacher sucks.
Your teacher does suck. I'm teacher.
But yeah, okay, anyways, I guess it does say it. But yeah, we went through all of these. Okay. Here, I think I gotta do this. Okay, yes. So what are the two elements in here?
Where?
Here, sorry. I know where to look, so I'm saying here as in, yep.
The F is fluorine.
Yeah.
And the Ca is calcium.
Yeah. So is that ionic or molecular?
We're sharing. No, we're sharing.
Is that ionic or molecular?
1 second.
It's
Where's the F?
ionic.
Ionic.
Where's the fluorine?
F fluorine.
Yeah.
Ionic. Good. So what's the name gonna be?
Okay, wait. Calcium's 2 fluorine. So it's gonna be calcium fluoride.
Yeah.
Yep. Perfect. And then the next one.
Molecular.
Okay, so yes.
Wait, H3.
P3.
pH3.
Phosphorus trihydride.
Yeah.
Yep. Nice. And then I have a video on the acid naming stuff. You guys have done acid naming?
Acids and
Like the
bases.
us and the ick?
Yeah.
Okay.
Acids and bases sucks. So much. I said acid. Oh no, I'm brain dead.
Why do you keep moving the sheets? Why do you keep taking?
What do you guys go into on acids and bases, like
Just the
mainly?
naming and then how like every acid has an H and every base has an OH and like.
Do you go into anything about calculating anything.
Polyatomic acids and binary acids.
Do you know like conjugate acid-base stuff? No?
I don't think so.
No? Okay. If I say things and you don't know what they mean, that's good, because then I won't talk about it. That's a lot easier. I just don't want to go in like, so it's just basically like the us and the ik. And I think 8 is 8 one of them?
Yeah.
Okay, yeah, perfect. So yeah, we'll just watch this video.
This is the moment you've been waiting for, to unleash technology at your fingertips and make an impression.
All acids begin with H in front or a hydrogen in front. That is your clue that it is an acid.
Okay, good. It's just 4 minutes.
There are 2 specific types of acids, ones with oxygen and ones without oxygen. The ones without oxygen begin with a prefix of hydro. That hydro is your clue that there is no oxygen. Your setup begins with your hydro as your prefix. Next, we'll have our root name of our element, ending in ic, acid. The acid tells us that there's a hydrogen in front.
I'll pause this so you have time to
Remember,
write down if you
hydro
need
just
it.
tells you there is no oxygen. For example, hydroiodic acid. Hydro tells us no oxygen. The acid portion tells us there's a hydrogen in front, and that IOD tells us the root name of our element
I have
or
a question. So if it's like, because if you use oxide, it has oxygen, but wouldn't you name it hydro something? Hydroxide.
I think she will go and talk about that in a little bit.
Did you not learn binary acid, polyatomic acids?
No.
So like that's just extra hydrogens in the front, like H2PO4 would be a polyatomic acid.
It's basically rings of polyatomic acids.
Oh, okay.
Mm-hmm.
Oh.
What's the strongest acid? Do you know that one? No.
Sulfuric?
That's actually a really good guess.
Is that not right?
I think it is actually. It might be. It might. I think it. Hold on. I don't remember if it. Let's see. Strongest acid. Which one did you say again?
Sulfuric.
Sulfuric acid.
Yeah.
I think it is because that's battery acid. Oh no. It's fluoroantimonic acid.
It's not even on here.
No, I've never heard of that acid in the world, like ever. I think, yeah. Yep, -12 pH. Isn't that crazy?
Holy.
Yeah, sulfuric acid. Wow, I'm impressed.
dying.
Sorry, are we good to keep going?
Yeah.
Okay.
Out your charges, and we'll get the friendliest of all the acids, HI or hydroiodic acid. Let's go in reverse.
I'm scared out of
Now
nowhere.
Given your chemical formula and asked for the acid's name. We have HF. There is no oxygen, so that tells us hydro. Our prefix is hydro. We'll take this sort of setup, just placing our root name of our element, fluorine, and you get hydrofluoric acid. Remember that acid tells us the hydrogen in front. There is no oxygen, that's why it's hydro, and fluoric just tells us that it's fluorine. Hydrofluoric.
So the root name makes sense and stuff too, where it's like you just take the "ine" off. Do you need me to like pause? Like, okay.
Like how I did it was if it ends in I, you just change it to hydro something ic acid, and then if it ends in something, if it ends in like 8, then it changes to something else.
I have it as I ate an organic apple despite it being poisonous, and it's like 8 equals ick and A equals S.
That's smart.
That's what my teacher taught me.
That's actually pretty smart.
And then
Wrote it on my arm.
we just learned it by the ending. Like if it ends in the word I, you change it to hydro something ic acid, and then if it ends in like something else, I just don't remember the other ones.
Yeah, that's how I learned it too. That's how I learned it too. Yeah. Yeah.
The second type of acid does contain oxygen. So our prefix is gone. There is no prefix for this second type of acid. Your setup, which once again has no prefix, it goes right into the root word or root name of your element, ending in us, acid. For example, if we were to have nitric acid, that us actually refers to ite, and our polyatomic atoms come back into play. We have nitrite. So whenever we're given us, it means ite. The acid refers to a hydrogen being in front. We'll have nitrite, which was NO2 minus charge, and our acid placing that hydrogen in front, balance out your charges, and we get HNO2. The next setup, jumping right into that root name of your element, ending in ic acid. For example, nitric acid. The ic goes with another polyatomic, which is 8. So ic goes with 8. Nitric tells us really there's a nitrate. And the acid, once again, just states that there's a hydrogen in front. We'll balance out our chart.
That's all you gotta know.
So this is, so far as
Yeah,
making
wrote down
parallels.
If it ends in ate, then it becomes ic acid, and then if it ends in ite, it becomes us acid, and then I is hydroic acid.
Yes.
I didn't learn this.
Me neither, I searched it up. My teacher does not help me at all. While she's teaching, I watch a YouTube video of exactly what she's teaching by someone else. I can't listen.
It's really funny.
She's so bad at teaching.
Oh man, hearing all these things makes me weird about all the stuff my students are going to say about me.
You're not like,
He didn't even know how many electrons were in the fourth valence shell.
It's not like we know.
what?
I said it's not like we know.
Yeah, we didn't know either.
Yeah, that's fair. All right, there's like a minute and a half. Let's see what she
And we
says.
get HNO3. Let's go backwards once again. We're given our chemical formula and asked to figure out the name of the acid. You're given H3PO3. There is an oxygen, which tells us there is no prefix. The H says it's an acid. This is phosphite, remembering your polyatomic atoms. PO3 is phosphite. Ite goes with us. We will have this sort of setup, and it actually is phosphorus acid. Be aware of this case. We added an R. That is just something that you have to know, unfortunately. In chemistry, this is how they name phosphorus acid. Now, if we're given H3PO4,
Instead of phosphorus acid.
there is another oxygen, so no prefix once again. The H tells us it's an acid. This is phosphate. The 8 goes with ic. Your setup looks just like this, and in this case we do add another R once again, so it's phosphoric acid. This is another type that we have to know. So for any sort of PO4 or PO3, any of those phosphates or phosphites, they add an R. To help you remember naming acids,
There we go. Nice and easy.
Did you ever do the thing where it asks you if it's like aqueous or solid?
Yeah,
Or liquid?
holy. That, like, how to use this
I don't
table.
remember.
This
Oh,
table-
solubility?
Yeah, using this table, she did not teach us that at all. It was so hard.
Okay, so
Is
How
that...
am I doing that?
like if it's
Oh,
down
that's-
there, it's, I don't really know.
Yeah.
All right, here we go. Your favorite. So now that we have naming down, that was okay. Naming is okay.
Yeah.
Now that we have all those like the little rules down, perfect. Every time I hear that like Android notification noise now, like
Yeah.
properties of acids. Ionic, so conduct electricity. Sour. They are less than 7 and can be negative. That confused me a lot on the test, or on a test one time where I was like, how can the pH be like -4? This makes no sense.
Oh, so it said -14. It was like before 7, 14 after that?
What?
Oh my god.
Yeah, like the sulfuric acid is like negative a lot.
That's a great answer.
I don't remember what it was anymore. What did it say? Like it was like negative.
I could see
Ah.
right now the quiz.
I could probably, I could probably write that.
Full marks for sure,
I've
yeah.
written sorry in advance on some of my quizzes, and I've written no chance, no shot,
Yeah.
sad face. I've written a lot of things, and on my bio, like one of my last bio tests, there was, you know what I did? It does the photosynthesis thing, and I didn't know it, like I didn't learn it.
Okay, yeah.
So it pointed to like a carrot, so I wrote carrot. And it was supposed to be like water or something.
Oh, I see.
That's funny.
So studious.
Big smarts.
I should have gotten that right.
I think so too. You were right.
Oh yeah, big L to the teacher for not giving you marks on that one. Yeah.
Some teachers, man.
Yeah, true.
This is my
But yeah, and then blue turns red for acids. Bases have hydroxide as a negative ion. Hydroxide is the most basic base, if I remember correctly. That's a funny thing to say, the most basic base. Yeah, it's hydroxide. So it's just OH is the strongest base, but H plus is not the strongest acid. Wow. But yeah, it's bitter, it's slippery like soap, like how soap is basic. The pH is greater than 7, and red litmus paper turns blue. I also found this video. Apparently you can use red cabbage instead of pH paper to test for pH.
I'm just wondering why I found this written all in bases but not acids. Doesn't make sense. You know what? I passed. Ask him. I don't know how, because I don't remember any of this.
Physics. Holy physics is the worst.
Dude, I'm not passing physics right now. It's going bad.
Like significant digits, like it's so easy, but I get them wrong every time.
Yeah, me too.
Every time.
Yeah, and then they introduced this thing called significant figures, which is the same thing but different apparently. That messed me up even more, because then I wasn't even sure, like.
And I can't even like round. I always round one question wrong.
Physics is rigged.
And instead of rearranging the formulas, I memorized all of them. I don't want to rearrange them. I don't know how, so I just memorized them.
Yeah, I'm also awful at that.
No, I mean like, okay, they have to give you like, velocity is total distance over total time, but how do you find total time? Instead of rearranging it, I just remember total time was whatever it was.
Oh no, like gravity is 9.81. Have you never seen that with the acceleration due to
Yeah, but
gravity?
where did you get gravity from?
Well, I don't know, like on MG8, like EP equals MG8.
Yeah, but how do you find M? Like if they give you the answer and they give you G and H, how do you find M?
I just rearrange it.
Yeah, I just memorized.
I don't know how you do that.
See,
I'm confused. What?
But have you guys like written this, if you wanted to write it?
I'll have it.
Like notes down good? I can
Yeah,
watch the video.
Read.
Word. About mosquito
This
spray?
is Protection, the everyday skin protection ritual that
Yeah, I think
protects your
that's
skin.
Sides.
Protection instead of protection. Protection, like they just invented a word instead of using. Okay, interesting.
From mosquitoes, pre-barbecue, pre-walk, pre-everything. Prevention is the best protection. SC Johnson.
Great.
Today on Sci Guys, acid-base indicators.
What are you? I'm just imagining his like brother or his dad was just pouring.
Welcome
in
to Sci
something,
Guys.
like-
I'm Ryan.
And I'm Adam.
Oh,
Today
it
we're
wasn't
going
his
to be
dad,
making an
at least.
acid-base indicator using red cabbage. Poiple cabbage. It's called red cabbage. It's poiple. Its name is red cabbage. Hoiple cabbage. An acid-base indicator is a solution that changes color in the presence of an acid or a base. It can be a sudden change at a specific pH or a gradual change through many colors as the pH changes.
The equipment you need for this experiment includes a couple of glasses,
A blender,
coffee filters,
and a funnel. We're also going to need a few ingredients from the fridge and pantry.
The items we need from the pantry are baking soda, vinegar, and distilled water.
The ingredients we need from the fridge include lemon juice and a red cabbage.
The last two items we need are ammonia and antacid tabs.
The safety equipment we're going to need today includes gloves, goggles, and an apron or lab coat to protect from spills or splashes. Also, since we're dealing with hot water and sharp...
So just so you guys know, that's way too much safety equipment. You don't need that if you're dealing with lemon juice. Like, if you get lemon juice on yourself, the lab coat, wow, so much help. Anyways, still wear safety stuff, but I also learned on my practicum, and this is something that I probably shouldn't be telling you guys, but I'm gonna do it anyways. So there was this like solubility thing where the teacher was like, okay, so we have this chemical and it's really toxic, so make sure you always wear gloves when you're like touching it and stuff. And it actually, all it was just blue sugar. It wasn't even the chemical in the first place. So it was just like being lied to about this dangerous chemical that's just, you could eat. Just Kool-Aid powder.
Teachers like wear don't wear open toe. What am I saying?
Don't wear open toe.
Yeah. There you go. And then like wear a hair elastic. I never do. I always wear these shoes.
Yeah, well, I mean, the stuff that you're gonna be like touching and stuff is 9 times out of 10 gonna be not toxic.
And I have mechanics, so they like made me put on the covers. So
Oh no.
so that's why we don't wear them.
But that I can, like, that makes sense, because if you drop a hammer, that would hurt.
That's a you problem.
It's a fun class. It's quite an entertaining class. Great.
That's good. All right, get back to this video, I guess.
Make sure you have adult supervision. So the first step for our experiment is to add 4 cups of
It's
warm
sure
distilled
that
water
adult
or
supervision is especially important.
If you're around here,
butter. Next, we add 2 red...
If you look like this ever, you are more than safe enough. Like, that's good. He's like...
If you're around here, though, you need adult supervision. You never know what you can do.
I'm pretty safe.
Are you?
cabbage leaf.
Yes.
Oh.
Put the lid on securely. Holding the lid, give it a few pulses.
I want to remind you guys, the only thing he's touched is cabbage and water. Like...
The second step in our experiment is to take your coffee filter in your funnel and place the coffee filter inside the funnel. This will help prevent any small pieces of cabbage from getting into our solution. Place your funnel and coffee filter over top of another container and pour your blended solution through the coffee filter. Make sure to take any large pieces of cabbage out before you start this filtration process. The third step is take your cabbage solution and pour it into several different glasses. Make sure to leave enough room for the rest of the liquid we'll be adding to test for pH. The first solution we're going to test is ammonia. When ammonia is added, it turns our solution a green color, which indicates
What
that it's
did they add for ammonia?
The second solution we're going to mix with our indicator is a little bit of distilled water mixed with baking soda. The baking soda turns our indicator blue, which tells us that it's a weak base. The next solution we're going to add to our indicator is tap water. Tap water turns our solution a very slight blue color, but it still looks like a shade of purple. This tells us that the tap water that we tested is slightly basic, but close to neutral. The fourth item up for testing are Antacid Tabs. When we add a tablet to our indicator, carbon dioxide is produced, and because carbon dioxide is acidic, the color changes to maroon. This is not the end of our color change. Once our solution is done fizzing, the other ingredients in our tablet cause the pH of our solution to shift slightly towards a neutral pH, which changes the color slightly purple. Vinegar is our next solution that we're going to be adding to our indicator. When we add
Yeah, that one didn't really look like it changed much.
vinegar to our solution, it turns a very bright red or pink color. This color change means that vinegar is acidic. Solution number 6 that we'll be testing is lemon juice. Lemon juice turns our solution a bright red or pink color, which means that lemon juice is also an acidic solution. Let's look at this experiment a little closer. First, let's look at what pH is. pH is a scale that we use to measure acidity. The lower the number is on the
What does pH stand for?
Acidity level.
So if you have a big pH, like let's say my pH is 12, is it basic or acidic? Basic, good. Think of pH as the power of hydrogen. Yeah, I don't know. That's just what my teacher said. And anyways, now you guys know
What
about.
does it actually stand for? Power of hydrogen.
That's literally what it stands for, yeah.
pH.
Because, so this is something you guys don't need to know at all, but it's on a log scale, which is something you learn in Math 30. Basically what that is the log is the opposite of an exponent. So you know how multiplication and division are opposites? Like a log, log, is a math thing.
Exponent division?
No. No. You don't need to know like any of this. I'm just like explaining why it's called the power of hydrogen. It's because it's technically you can derive the concentration of hydrogen from the pH.
Being AP math.
Apparently, I'm in hot good luck. I don't know what I'm gonna do.
Just drop out.
Elliot in Greek, his name can be calculated.
I didn't.
That's a lot of dishes to clean.
So I'm just getting blown away. There's like a touch screen on this Mac.
Is that not your Mac?
No, this one's mine. I'm just borrowing
There's
this one.
3 apples on it.
I know. There's stickers, yeah.
Are you sure you didn't do that?
Yeah.
I don't know.
Yeah.
I feel like if it was my computer, you'd be like, "I need 3 apples."
Why not stickers? Because they don't light up.
Well, yeah, I just thought it was funny. I got this computer when I was in grade 9. And I've been using it ever since.
But mine, grade 10.
Was that your first one pulling up slow?
I lost that one.
Oh no. Was it expensive?
Yeah. It's back.
That's a big oof.
Still the same computer.
Yeah. Well, they last forever.
Yeah, they should have.
Like, gee, well, I mean, yeah, that's kind of a little.
Did you lose it? Did you lose it in Canmore? Or this is someone else?
I think Kenmore, I think.
Water is a neutral solution and has a pH of around 7. Vinegar, which is one of the most common household acids, has a pH of 2.2. pH is determined by the number of hydrogen and or hydroxide molecules a solution has. One of the ways that scientists determine the acidity of an unknown solution is with a pH indicator. There are many different kinds of indicators.
I don't think you need to know. Oh my God.
On your 18th birthday, I will be exposing that in my speech.
You're not allowed to do that. So then I'll actually never speak to you. My mom doesn't know.
The rainbow, and each color has a different wavelength. Molecules of different shapes reflect, and these
Yeah, here we go.
indicators show the pH molecules the object is made of. White light contains every color in the rainbow, and each color has a different wavelength. Molecules of different shapes reflect and absorb different wavelengths of light. The wavelength of light that reflects off a molecule is the one that reaches our eyes, and that
So, judging by that, so what he just said was the wavelength that is reflected is.
I don't remember learning this.
What does he say?
light.
So for example, what that means is this TV is absorbing every single color that is being shot at it because it's black. But that shelf is actually reflecting every single color because it's white. Yeah. So like this is just reflecting red but absorbing like blue and green and all that stuff. Yeah.
Wavelength of light that reflects off a molecule is the one that reaches our eyes, and that determines what color we see, while all other wavelengths are simply absorbed. When we add an acid to a red cabbage solution, we flood it with hydrogen molecules, which causes the indicator to change shape and reflect red wavelengths, making the solution look red. If we add a strong base, there is instead a high amount of hydroxide molecules, causing the shape of the indicator to change color and reflect green or yellow light. Solutions that are only slightly acidic or basic will change the color.
Oh my god, it's so annoying. Sorry. But yeah, that's actually kind of cool. Sorry? It's just exactly where I normally put like my like these two fingers when I'm just chilling.
The really neat thing about our
It's like, nothing's working today. But yeah, that's actually I never knew that red cabbage was could be used as a pH indicator, but I guess now we know.
Because I'm totally gonna do this experiment at home.
Yeah, you're gonna be like, Mom, guess what I learned at tutoring today, all right? Look, do we have red cabbage? Actually, I'll stop at Safeway on our way home.
There's no Safeway in this building.
Just-
Tap, tap. I'll do it.
I mean, you were pretty close.
We were in Safeway actually.
Oh, you went in?
Yeah, I had an iced tea and
Yeah?
2 packs of gummies in my hands. And then I was like, wait, should we get pizza instead? And then we dropped it, and then we went to go get pizza, and Planet decided it'd be a good idea to run, and my ankle shocked, and I like fell.
So all of this was happening in like 10 minutes? Like tops.
We get stuff done.
Wow.
We're fast walkers.
Wow, yeah. I would have probably had time to like walk down the stairs by that point. This table is the one that you were talking about earlier though, right?
Bro, you're gonna bring your, I'm gonna print you one out.
Great, you're not complaining.
Like this guy.
Wanna hold my hand? Is that what you can reach me out?
So basically what this table is you can find whether or not a solution will be like actually work or if it will like not combine. Like for example, right? Let's say we had, let's do an easy one. Let's do this one, vinegar or acetic acid. So the fun part about this thing is that almost everything will dissolve in it. So that like when you see like the most.
Whoa.
Yeah, we don't have the same.
No, it is the same. It's just
No, it's
right
not.
here. CH.
Yeah, but you go down to this and it says AG, and we don't have AG here.
What do you have?
We don't have that.
Yeah, this is our table.
We have the OH one.
Yeah. Like we have cuckoo and then most.
No, we don't. We have OH.
Oh, so it's just a little different. So well,
It's different.
no, it's just a different author. Like this one might be older. I just found this one on Google Images, so it's.
You're joking.
What?
And you made me pay.
I had to pay for my parents' breakfast today.
I have to pay for my sister's birthday dinner tomorrow, so
Ooh, for your whole family?
yeah, we're going bankrupt. I have to pay for my sister, me, and my cousins.
It's a big bill.
It's gonna be a hefty.
I'm sorry.
Very hefty.
That's a lot of money.
Where are you going?
Texas. Bring your own food.
Yeah, you need a sandwich.
I don't have food at home. Okay. I just want Cajun chicken sandwich.
You got cactus?
Yes.
Yeah.
That's a good choice.
Hopefully, okay, my cousin's like low-key rich, so hopefully she pays for herself.
Or like Nika?
Yeah.
Not Jamie?
I don't know what she is, but
But yeah, anyway, so like regardless of anything, all you're gonna look at is if you get like a question where it's like, how soluble is this in this? You'll look at either one of them in this top row, or this top, what do we say it was? Column or row?
row.
Row?
I think it's row.
I think
and
it's
then
column.
You know what's
I'm gonna actually do that right now. Oh.
I'm telling you,
Okay, wait,
it's
so
row and column.
is this right? So it's like these are soluble with this, but it's mostly soluble with nothing, right?
Okay, so let's say this one is here and it's like paired with something else, right? If you see this, then it's soluble, and if you see a different thing, then it's not soluble.
So yeah, so basically, like if you like say we have like we want to see ammonium and something like.
Guys, I just wanted to let you know I'm right.
Oh yeah, I literally just looked it up too. It says solid row, and I was like, okay.
No,
Yeah,
row
these are columns.
and column. No, you said columns with this one, rows with that.
Okay, wait. So
You're
like
negative away.
the thing is like you have Ag, which means it's not soluble with Ag.
So,
You don't have that.
well, so it basically, honestly, mine is probably more wrong than yours. Is what I would come to the conclusion of, because this one has like no compounds in here, whereas yours does.
Okay, but look, like we have like this. So it's in the not soluble it has Ag and then cuckoo. So it would just be not soluble because it's Ag and then.
Oh, I see what you mean. So okay, so the reason that it's like, oh, I see where you're confused. Okay, I'm gonna go to this side because I want to write something down. Okay, so the reason you're confused is because there's the cuckoo twice.
Yeah.
So, because there's like this is one, right?
Yeah.
And then this is what you're like, okay, well how can, like, shouldn't they be really soluble? It's the same thing, like basically, right?
Yeah.
Well, no, because in a beaker, right? Let's just pretend we have a beaker. This squiggly line represents this. So in here we just have a bunch of this. So all of this water is, it's not water, sorry. All of this is this. Yes. And now what we're gonna do is we're gonna try to add this
The Ag. So if
in.
Ag
So it's not
is
soluble.
here, then it's not soluble.
So
But if it wasn't here, then it would be in the most, which means it's soluble.
So it's not soluble.
So if you didn't have the silver, then yes, absolutely soluble. It's like you're just adding water to water pretty much. Like, of course, that's not going to change anything. But what this does is in solution now, all you're going to have is you're going to have silver molecules. And they're not actually going to be ions, they're just going to be silver solid. Because what's going to happen is in solution, an ionic compound dissociates into this.
And then acids are aqueous, correct? All acids.
Acids are aqueous, so are bases. Because it's aqueous something.
Aqueous just means it's in solution with water.
Oh.
So like if you had like, so this for example, before adding this would not be aqueous. It would just be a liquid. Because it's just this, 100% this, right? But if you had like 30% this, 70% water, then it would be aqueous. So most times you will have aqueous in terms of acids and bases because just it's easier. But yeah, the reason why this is not very soluble is because silver can't dissolve in here. Like there'll just be a bunch of sediment at the bottom with just silver. So that's why it's saying that. So it's just kind of like the entirety of the molecule being able to dissolve. Wow. All right. And I was scared that we weren't going to make it in time. Look at this.
You were faster. Yeah. I would hope I learned all the material before my test.
Oh, you're a professional? You're talking to a professional right here. I did this PowerPoint this morning. What are you talking about?
See, here's what I do though. Because I'm in social, and Polina had social last semester. So I have her account for D2.
I did, because she kept asking me to set her revised habits. I was like, here's my password username. Take out whatever you want. Leave me alone.
So I literally paraphrase it on the day before it's due. I got a 94 on my last assignment.
you go, right?
Actually, no. The 94, I didn't even use hers. Because it was something that we had to do ourselves. Like, the art.
How good was my art?
No, I didn't use your art, though, obviously.
But how good was mine?
Yours was weird. It was like
It was a cult symbol. My teacher really liked it. He said it was unique.
Okay. Anyways, so I had to work that day. I got home at like 10, and I was high on sugar